In this experiment, we will review the mass spectrometry technique for using and analyzing unknown organic compounds. Mass spectrometry is a powerful analytical technique used to quantify known materials, to identify unknown compounds within a sample, and to elucidate the structure and chemical properties of different molecules. Mass spectrometry analyzes molecules and particles according to mass. A mass spectrometer has an injection port, an ionizer, an analyzer, and a detector. The mass spectrum can provide some information about a molecule. The mass spectrum provides information of the molar mass of a molecule. We can determine the presence of halogen or nitrogen in a molecule from the mass spectrum. We can also identify molecule structures by looking at the molecule's fragmentation. The determination of isotopes is also done using the mass spectrometry. Here is an example of a mass spectrum. This is a mass spectrum of ethyl bromide. The x-axis is the mass-to-charge ratio, m/z. With the charges often equal to the one positive charge, therefore the m/z value is equal to the mass of molecular ion or fragment ions. In a mass spectrum, the base peak corresponds to the most abundant fragment ion. The relative abundance of all other peaks is measured in comparison to the base peak. To determine the molecular mass in a mass spectrum is by looking at the highest mass or m/z value. This makes sense, because the highest possible mass should the mass of the molecule of interest, while mass lower than the molecular mass would be the fragments of the molecule. Therefore, the peak all the way to the right of the spectrum, at the highest m/z value, is the molecular ion mass or the M+. Except, there are isotopes present in the molecule, such as carbon or halogen isotopes. If the halogens present in the molecule, the molecular ions peaks will display a specific peaks pattern for different halogens. Here is the pattern of the peaks of different halogen isotopes. If the bromine isotopes present in the molecule, the molecular ion mass will show a 1:1 ratio for M+ and M+2. While chlorine will show a 3:1 ratio of M+ and M+2. For 2-bromine, 1:2:1 ratio, and 2-chlorine 10:9:1 ratio for M+, M+2, and M+4. Let's go back to the ethyl bromide mass spectrum example. Since there is one bromine in the molecule, so we will expect a 1:1 ratio peaks at the molecular ion peaks. You can clearly see in this spectrum, there is a 1:1 peaks pattern in the molecular ion peak. Therefore, the molecular mass of this molecule is the M+, which is 108 in the example and not the M+2 or 110. Next, the molecule is fragmented in the instrument due to the high energy. Fragmentation of the molecule in the mass spectrometry can get complicated, especially for the large molecules. Here, we will see an example of the fragmentation of ethyl bromide. One possible fragment is when the molecule loses the bromine ion, which gives up an ethyl ion. The bromine ion is also the possible fragment. The molecule can also just losing an electron, which ends up as a molecular ion or the M+. Another example, the molecule loses a methyl ion, which give up bromomethyl ion. The mass of these fragments can be determined by adding their atomic mass. For example, carbon is 12, and hydrogen is 1. Peaks at these fragments mass indicate the mass of the molecule or its fragments. For example, the peak at 108 mass is the molecular mass of ethyl bromide. Peak shows up as 79 corresponds to the bromide ion, and peak at 29 mass is the ethyl ion. You can find a table of common fragments in your lab manual on page 100. It will help in figuring out the possible fragments from the molecule in the mass spectrum analysis. To analyze your unknown samples, we have provided the mass spectrum for each unknown. From the spectrum, you can determine the molecular mass of your sample. Identify the presence of halogen by looking at the isotope patterns, and then figuring out the possible fragments from your unknown molecule. This information will supplement your IR and HNMR spectra, obtained in the previous experiment. Using all these three analyses, you can finally decide the correct structure of your unknown.